Hi everyone. Today I'm going to talk about our research work, compiling conditional quantum gates without using helper qubits. And we are Keli, Huang, and Professor Palsberg. We are from the UCLA Computer Science Department. So the goal is to persuade you that conditional gates can be compiled into codes of linear size. And we're going to go through 3 points to support that. The first point is that the challenge here is to compile conditional gates without using helper qubits. And that is the main challenge we're taking on in this paper. The second point is that in our paper, our compilation scheme is linear. And the third point is that, as our experiments show, our method is the best for 8 qubits and up. So we're going to go into that. First, let's go into the challenge. The challenge has to do with the conditionals, so we can take a look at the conditional gates in classical computing. Here is an if and else statement with 2 Boolean variables, B0 and B1. If they are both true, then we do the Boolean negation on the Boolean variable B2. That's the normal way as we all know it. In quantum computing, we have something like that, and we want to compile it. But the question is, how can we compile it? These conditionals are used everywhere. To give you the sense of the place it is used, here is the Grover's algorithm. The point is that in the loop body of Grover's algorithm SG, there is something called Z0 and ZF. Those are high-level gates. And the natural way to implement them is to use conditional gates. So then we can ask, OK, how can we compile it? It turns out that if we go to Qiski, which is the IBM popular framework for quantum computing, Qiski compiled those conditional gates using the universal gate set defined here. There are 3 kinds of gates here. And we're going to do the same thing as the IBM does. We're going to compile a conditional gates using this gate set. But our goal is to use as few gates as possible. The only thing to be aware of here is that CX now is a 2-qubit gate, which means that it is a 4x4 matrix. The U gate, that is a 1-qubit gate, which means that it is a 2x2 matrix. And the RZ is also a 2x2 matrix. When we count the gates, we actually only count the first 2, which are the CX and the U gates. This is because we don't count the RZ gates. This is because RZ only changes the global phases in quantum computing. But we put the RZ gate here is that we want to make the compiled circuit exactly equal to the source circuit. So we put the RZ gate here to achieve that. So then one can ask, OK, how good a job can we do? Of course, in classical computing, we're used to the fact that we can compile a large conditional using a linear number of conditional gates. For example, here, for this if and else statement, we can compile it using the conjunction of 2 if and else statements, and that is absolutely a linear way. In quantum computing, until 2015, it was not even known how to compile a large conditional gate using a linear number of gates. The previous best scheme generated a quadratic number of gates. Craig Gidney showed that in 2015, we can compile conditional gates using a linear number of gates. But the constant number is really large. It is 822. So this would mean that even though conditional gates are popular, they are also expensive. We absolutely want to continue on the challenge of no helper qubits, and a linear number of gates in the implementation, but we want a lot less than 822. So this gives us a chance to talk about our second point, which is our compilation scheme. Now I'm going to introduce our compilation scheme in a few steps. The first half of the idea is to do a little trick. In quantum computing, we can always have something like the square root of x. So in the compile code, we have that if Q0 is true, then we apply the square root of x to Q2. If Q1 is true, then we apply the square root of x to Q2. And we can see that if they are both true, then we actually apply the square root of x twice on Q2, which as a result, we apply the x gate to Q2. If they are both 0, then we do nothing on Q2. For these 2 cases, it looks like we are actually implementing the quantum conditionals. However, if Q0 is equal to 0 and Q1 equal to 1, or if Q0 equal to 1 and Q1 equal to 0, our compiled code doesn't work. For these 2 cases, if only one of them is 1, we actually want to do nothing on Q2. So our next step is to hack this code a little bit. And then we get exactly our compilation scheme for 3 qubits. What we do here is that we still keep our statements about the square root of x gate on Q2. But now I'm going to introduce the idea of +1 and -1. And I'm going to do +1 and -1 modulo 4. And I'm going to gently change the order of Q0 and Q1 and think of it as Q1, Q0. Now if we go through these 5 steps in the compile code, we can actually see that it actually implements the quantum conditionals as we defined before. If you understand this example, you will understand the whole paper. So let's go through each example. The first example is that, the first case is that Q0 equal to 0 and Q1 equal to 0. The first 2 lines of code do nothing on Q2, and the third lines of code adds 1, and then we get 0, 1. The fourth line code is conditional on Q1. Now Q1 is equal to 0, so we do nothing on Q2. And the fifth lines of code is doing a -1. And then we get 0, 0. And we can see that if we have 0, 0, we actually do nothing on Q2. The second case is that Q0 equal to 0 and Q0 equal to 1 and Q1 equal to 1. The first 2 lines of code implementing the X gate on Q2. The third lines of code add 1, and then we get 0, 0. The fourth lines of code is conditional on Q1. Now Q1 is equal to 0, so then we do nothing on Q2. The fifth line brings us back to 1, 1. And we can see that if we have 1, 1, we actually apply the X gate to Q2. And the third example is that if we have Q0 equal to 1 and Q1 equal to 0, the first 2 lines of code implementing the square root of X to Q2. And the third line adds 1, and then we have 1, 0. And the fourth line of code is conditional on Q1. Now Q1 is equal to 1. Then we apply the dagger of the square root of X on Q2, which cancels out with the square root of X we introduced before. Now the fifth line of code brings us back to 0, 1. We can see that different from the thing we introduced before. If we have 0, 1, we actually do nothing on Q2. The story is the same for the false cases. If we have 1, 0, then we do nothing on Q2. So this is our compilation scheme for 3 qubits. And let's now go look at our compilation scheme for n qubits. Here is a general scheme for n qubits. Here we have a large +1 gate here. Here we have a large -1 gate here. And here we have generalized gates here. What they do is the same as we introduced before, but now they are using roots which are beyond the square roots. In our paper, we actually proved that our compilation scheme works. Now our compilation scheme uses 278 n gates, and our constant number is only a third of the previous best scheme compared to the previous best scheme. So this is our compilation scheme. Then we want to ask, okay, how does this work in the experiment? We have 3 questions to ask. First, does it reduce on the code size? The answer to this question is yes. Our compilation scheme produces code that is 34% compared to the previous best scheme once we go to 23 qubits and above. The second question is that, can a quantum circuit optimizer help achieve our results? This would mean that you take the Kragini scheme and then you apply a really good quantum circuit optimizer. The answer is no. Even though after optimizing the Kragini scheme with the quantum circuit optimizer, our compilation scheme still produces code that is 49% as large as that produced by the state-of-art and the optimizer. And the third question is that, can the output from our compilation scheme be further optimized? The answer is yes. You can take our compilation scheme and run it on a good optimizer. The code will be 80% smaller on average. So let's see those things on graph. The first graph is about the code size. We're comparing 4 methods here. The green one is the best one from Qiskit, and it is exponential. The yellow one is from the Baranko's paper, which is considered to be the best one before the Kragini scheme, and it is quadratic. The red one is from the Kragini, and it is linear. We have differences between odd and even numbers because they have different implementations. And our compilation scheme is in purple. It is linear, and it is better than other compilation schemes. The second question has to do with the quantum circuit optimizers. And here we list 7 quantum circuit optimizers that we experimented in our paper, including Qiskit's own optimizer. We found out that the VLQC from the POPO 2021 is the best one. It optimized the Craig-Gidney scheme the most. So if we take a look at this graph, we have our compilation scheme in purple that we introduced before. Now the red curve is about the Gidney scheme and the VLQC optimizer. We can see that even though after optimization, it is still well above our curve, and the optimization rate is around 30%. And the last thing is that, of course, you can use those optimizers to optimize our compilation scheme. The thing is that if you take the VLQC optimizer, which has the biggest effect, now our compilation scheme has the constant number down to 228. In the worst cases, before it was 278. So our conclusion is that first is that our compilation scheme produces code that is 34% compared to the previous best scheme. And second thing is that you can not use the quantum circuit optimizer on the previous best scheme to achieve our results. But of course, you can use those optimizers to optimize our compilation scheme. We think there's a lot of room for improvement here, and we strongly encourage the PLDI community to contribute more on the quantum circuit optimization. The last thing is that our compilation scheme is really simple to implement. It only contains 5 steps to implement, and we strongly encourage you to try it on your own quantum compiler. And that's all. Thank you.
Thank you. So we actually have a bunch of time for questions. So go ahead.
Can you go to the previous slide?
This slide.
Yeah. So here you're saying like it's maybe 215 instead of 270, but then how is that 30% of the previous best?
What was the?
You said that your tool achieves a size which is 30% of the state of the art, but then in the
this one is the previous best one.
But in the second last slide, what was the 278 then?
You can think of in this way.
Oh okay.
278 is our compilation scheme.
Now I got it.
The 228 is our compilation scheme plus an optimizer from the previous work, from the optimizer work.
Is my understanding correct that this approach only works for classical control?
For classical control, what do you mean?
That the controls are not in a superposition. Okay, it's just the examples you show are only that, and so it still works with the addition and mod 4 operation. Okay, well, I would like to see the details on that then.
Hi, excellent talk. I like the way you explained the example. You showed 3 questions. No, the 3 questions that you had. Yeah. So the second statement, is that really right? That no optimizer can achieve your results? Or is it no existing optimizer can achieve your results?
At least we tried these 7 optimizers. They cannot achieve our results. And the VLQC one is the best one. And it cannot achieve our results. Yeah. I can guarantee that. I tried all of them. I can guarantee that.
No existing.
No existing, yeah. And I think there's one more research work which is called CRO, right? And we do not try those things. CRO uses reinforcement learning in quantum circuit optimization, but we don't have the the resource to do reinforcement learning. Yeah.
Hi, just one question. You mentioned something about your scheme performs really well after 8 qubits, and that's when it shows optimality compared to other schemes. So just curious, does something different happen on when you deal with smaller controlled gates, or is there a more different optimal way of compiling them down or implementing them in general? Or was it just that there's somehow special cased and in these?
Once again, I actually don't understand what you're asking.
Oh, sorry. So I was just saying that you mentioned that your scheme particularly performs really well after 8 qubits in comparison to Qiskit's compiler, I think.
Yeah.
So I was just saying, does Qiskit do something special or special case them before 8 qubits to achieve those results, or is it something like that?
I can give you the Qiskit. If you have qubits smaller than 8, Qiskit exponential methods actually produces code that is smaller than our compilation scheme, but it is exponential. It means that it grows really fast. But you have when the qubits is really small, it actually uses fewer gates to implement. We think that it do not, and we just cut it off and started from the 8. Yeah.
Okay.
So I was surprised with the list of optimizers, and you said that Vox was actually the most efficient. And Vox is an implementation basically of Nam et al.'s compiler from a few years even before that. And I thought that, PhysiX, among others, was, as we saw in Charles's talk, doing some additional stuff in terms of a more powerful version of what amounts to rotation merging. Were you getting similar results for Vox, Quartz, PhysiX, and others, and it just happened to be like Vox was reducing 1, or like by 1 extra, or like how did they actually compare in practice, optimizing your tool?
Let me rephrase the question. Is Vox a lot better than the other ones, or is just a little better?
I think Vox is, VOQC is a lot better than other one. It is probably not that better from ticket, I think, but I think it is I can guarantee that it is a lot better than Quartz or PYZX or Qiskit, yeah. Because I think these two, especially for Quartz, they are especially targeting the arithmetic circuits, which is not our cases here. Yeah.
Okay, thank you.
I mean, why VOQC is better probably have different reasons, but I think the result is that VOQC is better than all other methods.
Yeah, that's surprising to me because they're very similar in terms of what they do.
And me and my advisor is also surprised because VOQC is not generally considered to be the best one. Mm-hmm. Yeah.
Yep. All right, let's thank our speaker again.